talk is about just that, combining what's above the ground with what's below the ground. And Tom is the gentleman over there, and I am Doria Katrubis, as you already know. So we're going to go basically into what is LiDAR, what does it do, and then we're going to go a little bit into GPR. That's the bad news, because, you know, when Tom couldn't present it here in person, he's like, okay, you got to talk a little bit about GPR since you're here. And that's good, because I don't like a little black box presentation about GPR. LiDAR, and we combine the two. We use the example of Truro Park, and Newport Tower, even though we have done this with other sites. So again, we'd like to thank NERA for the funding that allowed us to do this, to do both LiDAR and GPR of Newport Tower. So what is LiDAR? It was invented in the 1960s. And basically, it was used for satellite applications, and it was used for, you know, high elevation satellites. And then, as we came back down to Earth, we found that there were all sorts of other new applications. And there's 4 different types, general areas of LiDAR. There's airborne LiDAR. There's drone or UAV type of LiDAR that's on these drones. There's terrestrial or tripod mounted LiDAR. And then there's the mobile and handheld LiDAR. And each of those has an application. Like, for instance, you can't picture Tom walking around with this 3D handheld LiDAR in the middle of the Mayan desert, the Mayan tropical jungle. So with the airborne LiDAR, you know, initially you were getting, maybe 4 to 6 scans, you know, points per square meter. And now we're up to maybe about 400 to 600 points per square meter. That's a big improvement, 100 times. With the drones, their accuracy is improving too. You get about 100 to 700 points per square meter. And the accuracy is, you know, up there, 3 centimeters to 10 centimeters. With the tripod mounted or the terrestrial LiDAR, this is used more in construction to verify or design to verify bridges before they're built. And they're really, really super expensive systems, and they're very, very accurate. They're within a millimeter accuracy and like 500,000 points per square meter. It's pretty cool. So these are other examples of mobile and handheld LiDAR, and they're about 300,000 points per square, points per second, excuse me. And of course, you are very familiar with Tom and his 3D LiDAR surveys, and he gets about 150,000 points per square meter the way he walks. And it's basically mounted on a tripod as he walks around, and he does lines that are, you know, every 8 to 10 feet apart. And he's able to capture things out to, 80 feet on either side of each traverse. So why use mobile or handheld LiDAR to document these ancient sites? Well, this is a kind of a no-brainer, because you can tie the LiDAR with the GPS, and it provides a real-time ability to capture these. And you are able to get rid of the vegetation. So a lot of these sites are overgrown. So you're able to see alignments and things like that we wouldn't be able to see. And you're able to geo-reference everything. So it's proof that we can bring to the SHPO, that, hey, we really do have something here. It's not in our imagination. And it is probably the most versatile way of documenting these sites, other than, say, 3D photogrammetry. And below, you see a LiDAR scan of Truro Park of what's above ground. And we're trying to combine this, what's below ground. Enter ground penetrating radar. Well, radar has been around since the mid to early 70s, mostly for military use. But now, since like the late 70s, early 80s, it developed many commercial uses. What it does is it uses microwave energy and radio wave energy. So basically from, say, 100 megahertz all the way into the gigahertz range. And what it does is it transmits these signals into the ground, and not at the operator, because it had this nice shielding on top. You don't want to zap the operator. And it detects the reflected energy from anomalies. And mostly what causes these reflections are small and subtle changes in the electrical properties or the physical properties of the material. And the electrical properties say conductivity, how conductive it is. So the radar system does consist of 3 different components: the control unit, which is what that gentleman is looking at, the antenna, which is those in the yellow box there, and the cables that enable them to talk back and forth to one another. So the metal targets are really easy with the radar. Again, many commercial uses: underground storage tanks, utilities, that sort of thing, rebar to verify, how something is constructed, like a slab. What we look for in the archaeological world are voids. Basically, organic matter decomposes. And so it creates spaces, and the GPR is going to pick up on that. Why? Because there's not only like a greater amount of moisture in there, so that's kind of reflective too, but it's less dense. So there's a couple different reasons. And radar is also good in mapping stratigraphy, as well as changes in water table. So this is what a typical radar antenna looks like. It has a front lobe and it has a back lobe. And it typically looks about 5 feet in front of the fore and aft of the antenna, and about 2.5 feet, 3 feet side to side from the antenna. So this creates an interesting kind of response. People expect to see, you see this little, on CSI, oh, there's a skeleton right there, there's a scapular, no, that's not what we see. What we do see is, here is the real life up here. There's a cavity, there's a lens, here's the interface. And what we see is sort of like a little, we call it a hyperbolic type of reflector. We see a flat reflector from the lens, and we kind of see more or less the shape of the stratigraphy. So yeah, you can figure out what's what, right? So each wave looks like this. This is your transmitted pulse. And then all this gobbledygook below there is reflected energy. And that is really simple to interpret, right? No. Yeah. So what we do is we colorize that. Say the red there is 0 amplitude. So you have a wave that has positive amplitude and negative amplitude, and we shade, each of these little incremental amplitudes with a certain color. In this color transform, white is the highest amplitude and gray is the lowest amplitude. And the brown and the black is near 0 amplitude. So as we go over the target, you're detecting the, remember, 5 feet ahead of you, you're picking up that target, and your horizontal scale here is your distance. And your depth scale here is your vertical axis. So you're picking it up far away. It's really a two-way travel time. So radar waves are bouncing, hitting the target, coming back. But as the antenna is moving, you're right on top of it. So as you're getting closer and closer to the target, that's where you see the crest of the hyperbolic. And then you're moving away, right? So now you know what that is, right? No, that's actually an underground storage tank. Could look like a utility, could look like a void, could look like a boulder. So, okay, we still need a way, instead of always like visually inspecting radar, it leads you to a lot of frustration because it's subjective as hell. So here we go. This is our second method of interpretation. And what we do, and I apologize for its small little squares, each radargram, again, this is distance and this is depth because we assign a velocity to it. And we take each little cell here, which is an incremental change of horizontal X and vertical Z, and we find what that velocity is and what that amplitude is, and we save it into an array of a computer. So, okay, we now know that that particular cell has a certain amplitude. And then what we go and do, here's our line that we're on, and it says, okay, let's look couple cells forward, couple cells back, couple cells down, and let's look at the next line and the next line, and we'll go across to it. And so then the program takes like amplitudes and shades them similar colors. So the highest amplitudes are the reds and the oranges and the yellows, and the lowest are the dark blue. In this particular instance, we're missing data where it's white, and we're looking for a water leak. And that little cyan colored line is a little pipe, and that's another little pipe, and that's where it broke, and that's where the water is spilling about 2,000 gallons per day. But this is an example deliverable for all you landscape architect folks. This is the James Arnold Mansion. And for all the Massachusetts folks, the Arnold Arboretum. He was the gentleman who had such a fun time doing landscape architecture at his own home in New Bedford. He decided to gift the city of Boston with a similar type of arboretum. But what these lines are the old bedding, the former landscape gardens that he had, which is really kind of cool. You can detect really subtle features from here. In this particular survey, not shown, we also found where the outbuildings were. So, as I said all along, Tom and I have been working, really Tom trying to nudge me in the right direction. Hey, let's combine them too. So off we go. And Tom, can you talk about this or?
Sure, I can talk. So the approach at the Newport Tower was we were hired by NERA independently of each other, but because of our relationships, we've continued to work together to try to combine the datas. And so our work at the tower was non-invasive. Our technologies are non-invasive. So there I am on the left with my scanner on a small pole just there above my head. Sam is pushing the radar unit. And then in the scene on the right, Sam is taking GPS points for me so I can georeference my LiDAR data to Doria's GPS points, which are real world points. And so that way we're able to provide information that would fit into Google Earth or any other georeferenced data set. So Newport Tower is within Turo Park in Newport, Rhode Island. The image on the top there is an oblique view of my LiDAR scan with a black background so that the features jump off the page. But with the third-party software I'm using, the Vision LiDAR, it enables me to pretend as if I'm flying through and over and across the landscape. Hence, the scene on the bottom is a cross-section, again, of the scan, but manipulated in a way to create a cross-section. And as a landscape architect, that cross-section on the bottom would take me half a day. Once my data is captured, that took about 15-30 seconds. Zooming in closer, this gives you an idea of the resolution of the scanner, 300,000 points per second, 150,000 points per square meter. Not photographic, but a heck of a lot better than the aerial and the drone LiDAR, only because of the height and the speed that they're flying. And so with this, Dory, I wanted to let you know, run this video through the whole length because you've got 3 different animations in this one video. And so you can talk about your data here. Now, so bring your cursor here. Yeah. And so now we double clicked.
There we go. So what you're seeing is all the reflections in this color transform where the red is the highest and then the yellow and then the black. What you're looking at are a combination of boulders and areas of excavation.
What's the maximum depth?
In this particular instance, I think we went down about 7 feet.
Doria, I want to stop this for a second. So
Okay.
3 years ago on the first project that Doria's team, specifically Cameron, Russ and I worked on a cemetery in Long Meadow. He presented his data, which is similar to this, to the client. I was so impressed. I asked so many more questions than the client because I saw so much application. And as you look at the red anomalies here, the red reflections, I said to Cameron after the meeting, how can we get your data into my software? I want the red, which I jokingly say is the fruit in the Jello fruit salad without the Jello, which is all the other colors. And at the end of the presentation, you'll see what I mean.
On this diagram, true north is where relative to the grid?
That is a very good question, which is why everything needs to be geo-referenced. So you're looking at the raw output from GPR slice. So is there a way I can advance this?
Yeah, but you're gonna fly through 2 other animations.
So right here, we're looking at surface level.
So right here, I'm going to pause it again.
Yep.
So where it says depth over here, you're looking at a slice that is from the volume 1.3 to 1.7 feet below grade. And what I've done with these lines here is I've assigned a depth range to them. And it's the outline of where I think the boulders are from beneath each column.
And the 8 numbers represent the 8 columns of the tower.
Right, and the gate is between 1 and 2, so that's north on the thing there. So I'm gonna set this going again. So it's going from top to bottom, bottom to top, and
the boundary is the edge of the octagonal sidewalk.
so yes, in this particular, the fencing, I believe.
That's
Yeah, so these are each of the columns. So you've got the grass inside and you've got the iron rod fencing on the outside, which metal's reflective. So you can actually pick up, some of those reflections from the side. But the thing about the columns in GPR, physically the GPR could not get right up to the columns. We had to use a different GPR system because it allowed us to get within 6 inches of the column. The physical housing, again, GPR will project a few feet forward and aft, but physically the housing was being blocked by the column.
Can you run that in? Yeah.
Hey, Dory, we got 10 minutes left, so we need to run this.
Okay,
No, let it run because the next animation is good too.
okay. So the other thing you are picking up are the excavations. So this particular site was used since 1950. Other archaeologists came and they did digs and they did test pits, and we pick up that. So it's kind of hard sometimes to see the forest through the trees. All right, and then I guess this is the last one for this one, where we're just showing the outline. And then as we're going down, slicing down and coming back up. So again, the light pink is the topmost outline of the boulders, and then we're just continuing on down.
And the idea for the 3 different videos was to illustrate how Doria can present her data in a multitude of ways. That's the idea.
So,
Explain what we learned about the excavations from this. I was trying to read your thing to see what parts were actually excavated and what parts weren't.
so what we learned is that the reflections from both the excavations and from the boulders, the goal was to see how the tower was constructed, how it was supported. They knew nothing about how this tower was supported, let alone who built it. A lot of different theories. And this is, the radar will show the reflections from where it's been disturbed before, but also it's showing where the boulders are. And with radar, you need context. So by combining the LiDAR with the GPR, it gives the GPR context. It's a very powerful tool. And so you can kind of see the shadow of the thing, and you can kind of see boulders underneath. This kind of appears as a continuous layer. I will show more there. In this particular visualization, this is from the top looking down. Again, this is the LiDAR, and you can see stuff interior is really from just the excavations. It's a shallower depth slice. And then the nice thing about combining both the GPR and the LiDAR is you can kind of look underneath. The yellow represents like one of the high, in this color transformed, one of the highest reflections. So you have, boulders there and boulders there, and you get a column there, and there's an enlargement of it. I mean, that's the neat thing about the LiDAR is that you can zoom in, you have 300,000 points, so you don't lose resolution when you zoom in. Here is another shot. Again, here's a tower. Here's a cluster of, here's a cluster of boulders, another cluster of boulders beneath that column, another cluster of boulders, so every column you can see an area of higher amplitude reflections beneath them. Remember when I said, oh yeah, that looks like a horizontal layer? The first survey we did find a horizontal layer. I thought initially it was bedrock, but it looks like that there is like in between the columns, there's like another layer of small stones to level out at about 4 feet or so, maybe a little bit, just under 4 feet in the middle of it. But it's like a pedestal built of small stones with the larger boulders at the columns. And again, that's from the radar. And this here, you can see how that, that layer appears. And these are other examples. Okay.
So extending on the top side of the tower, left-hand image, a little sweep out there. What are those artifacts?
So right now you're looking at the top of a layer, a stratigraphic layer, which I believe is, flat stones, like the flat stones are here at about 3.5, 4 feet. And then it drops off to 4.5 feet, 5 feet, and then it's deeper over to the northeast. What this is over here, I'm not quite sure. We have depth slice images actually past the sidewalk, and whether there are post holes there from an awning, sometimes I see there's something there and sometimes I don't. Not enough to, I'd probably have to do a little bit more, work there to really investigate it. So one more view of the different aspects of presenting it. And then this is an embedded video also.
So again, here is the LiDAR scan of the park, and it'll transform to RGB color, which you see here, to color by class. I'll turn the classes off, on and off, and we'll end with a few seconds of the tower with the GPR underneath. And, I included this for those of you who haven't seen my LiDAR and what the software can do, give you some indication of the power of the two. With the software, I can isolate individual features and turn everything else off. And so what I'm doing now is isolating the tower.
And that's the radar underneath it.
Yeah.
That's that layer I was telling you about.
So the fence was classified, turn that off. The ground in my LiDAR was classified, I turned that off. The ground in Doria's GPR work was classified, I turned that off. And that array of colors is the ground penetrating radar data. And what you'll see here is I'm going to isolate even more of this and then turn off the Jello out of the fruit salad. And on February 6th of this year was the first time we were able to accomplish this goal. It took 3 years to figure it out. And so what you're looking at here, extrapolate this to any other site that you might be working on or investigating and figuring out, well, if I had LiDAR, what could we do with it? And if I had ground penetrating, what could we do with it? Well, we've shown you the power of our technologies and our software in this presentation. And so there's the fruit in the Jello salad.
Is there any intent to expand the circumference around the tower outside the fence?
The question was, is there any intent to expand the survey outside the fence? And that is up to the powers that be at NERA.
Well, but the purpose of the work was to do what we did to try to support the investigation by NERA for OSL dating at the base of the columns, to try to date it and therefore possibly figure out who may have built it.
Great, but we do have, there's data that we fused together because the GPR extended outside in a larger swath outside the center area of the tower, correct?
Yes. So the outside the area, there's another data set that was GPS guidance only, which had some issues with it. So we would probably want to set up a grid. While we're very good with GPS, with Canopy, it's not so good. Yeah.
So that ends the GPR and ground penetrating radar and the LiDAR. And now I want to do is take a couple seconds to introduce you to the new technology I purchased at the end of last year. I purchased the Insta360 Titan, which is a 3-dimensional, 360-degree professional grade camera that captures individual pictures and videos. It has 8 lenses, 200 degrees fisheye lenses. Photographs are JPEGs and DNGs. Videos are MP4 and HOVs. Has 9 onboard SDR cards or SD cards, and it weighs 12.1 pounds. But what's really interesting is I can set this up to download or upload to Google Street View and have it be on Google for Street View investigations. But also it's ideal for VR headsets, in-depth and immersive tours. And that's what the camera looks like. And so, 37, Dora.
Okay.
And so here to end on is a video of a 360-degree camera, and it's literally 360 degrees above, to the sides, and below. And this is a site, Manitou Hashnash Preserve in Hopkinton, Rhode Island. And, this is just to give you an idea of the resolution. It's 11K in resolution, and we can spin it fast, slow, up, down, zoom in, zoom out. But what I cannot do is I cannot change my elevation of the viewing like I can with my LiDAR scanner. So it's a fixed elevation, but I can rotate it in any of the 360 degrees. And we had another video to show you what a video of a video would look like, but we just didn't have time to include it into our presentation.
There's a question out back. Tom, are you ready for us to have questions?
Yeah, go ahead. Yeah. Let this play though, but ask questions.
Okay.
Hey, Tom, it's Glenn. I don't know if you can hear me. The question is, you're prepared to say that we see elements of the foundation of power in that GPR scan?
So Glenn is asking, is it fair to say that we're seeing elements of Newport Tower in the, beneath each column? The foundation of the tower. I would say yes. I would. That would be my bet. It's too much of a coincidence. There's a thank you slide.
That was it.
Yeah.
Yeah, there was a thank you slide. That was it.
That was it.
All right. Thank you, everybody.
Thank you.